In cross-view geolocalization, retrieving a satellite image that matches a drone-captured query, there's a fundamental challenge that's often overlooked: hard negatives. These are images that don't belong to the same location, but look almost identical, structurally, color-wise, even architecturally similar. And in feature space, they can end up closer to the query than the true positive. This misleads the model, corrupts gradients, and destabilizes training. It's like trying to find your friend in a crowd where someone who looks just like them is standing right next to you. Easy to get confused. Existing methods try to fix this with hard negative mining or loss reweighting. But most rely on static rules, assign higher weights to difficult samples based on a fixed margin or a threshold. The problem? That approach fails under real-world distribution shifts. A sample that's hard in one scene might be easy in another. Worse, clipping strategies collapse all extremely hard cases into the same weight, erasing fine-grained distinctions. And worst of all, they apply this heavy emphasis too early, when the model's representations are still raw and noisy. That's like turning up the volume on a bad microphone during a rehearsal. More noise, not better sound. So how do we solve this? We introduce dual-level Progressive Hardness-Aware Reweighting, or DPHR, a two-pronged strategy that adapts not just to difficulty, but to when you're training. First, sample-level reweighting via the ratio-based difficulty-aware module. Instead of using a fixed threshold, we compute a relative hardness score for each negative sample. The key idea: how close is the negative to the query, compared to how close the true positive is? We define this as high k equals d p letter 1 d62 chi. That's the distance from the query to the positive, divided by the sum of that distance and the query to negative distance. If the negative is very close to the query, this ratio approaches 1, meaning it's a hard negative. If it's far away, the ratio drops towards 0. This ratio is scale-invariant. It doesn't care about global feature norms. That's critical because embedding magnitudes can drift during training. So we map this score linearly into a weight interval, say, so that harder negatives get more influence but not too much. Now the second layer: batch-level progressive weighting through the progressive adaptive loss weighting mechanism. Here's the insight: early in training, you don't want to trust the hard negatives. The model hasn't learned good features yet. So instead of applying full reweighting from iteration 1, we use a training progress signal derived from recent unweighted triplet losses. Specifically, we compute a moving average of the past few losses, say the last 100 iterations, and normalize it into a range. When training is unstable, losses are high and fluctuating, the normalized signal is large. That means we're still in the noisy phase. So we suppress the impact of the reweighted loss. As training progresses, the loss stabilizes, the signal drops, and we gradually unmask the hard negative weights. We formalize this with a scaling coefficient lambda t, which starts low, say 0.2, and increases to 1 over time, controlled by a smooth exponential moving average. This ensures that the model first learns robust, generalizable features, and only later focuses on the fine-grained distinctions that separate hard negatives. The final loss becomes LDPHR equals L tri plus lambda t times LW tri. So the model starts with a stable, noise-resistant objective, and as it matures, it progressively sharpens its ability to discriminate between visually deceptive but geographically incorrect matches. Now let's see how it performs. We tested DPHR on 2 major benchmarks: University 1652, which covers 1,652 buildings across 72 universities, and SUSE 200, a challenging dataset with drone images taken at 4 different altitudes: 150 m, 200 m, 250 m, and 300 m, paired with satellite imagery. We integrated DPHR into 3 state-of-the-art models: LPN, MCCG, and Sample 4 Geo. The results: consistent, significant gains across all retrieval directions, drone right arrow satellite and satellite right arrow drone, and across all altitudes. On SUSE 200 at 150 m, where viewpoint differences are extreme and discriminative cues are minimal, Sample 4 Geo's R at 1 jumped from 86.23% to 94.55%. AP improved from 88.55 to 95.6. That's over 8 percentage points, a massive leap in a task where even 1% is hard to gain. Why? At low altitudes, the ground footprint is small, and buildings appear more fragmented. Hard negatives abound. DPHR doesn't just find them, it weights them appropriately, amplifying informative contrasts while suppressing early-stage noise. Even in high-altitude settings where images are more similar, DPHR still improves performance, just by a smaller margin. Because the relative difficulty of negatives is lower. So the system naturally scales its attention. We also ran an ablation study using MCCG as the baseline. Without RDA or PALW. Baseline performance. With RDA alone. Performance dropped. Why? Because we were emphasizing hard negatives too early, before the model could handle them. The gradients were noisy. With PALW alone. Improvement. It suppressed early noise and let the model stabilize. But only when both RDA and PALW were combined did we get the best results: 29% R at 1 and 90.97% AP in drone right arrow satellite retrieval. This proves the synergy. PALW ensures robustness early on, while RDA enhances discriminability later. They're not just additive, they're complementary. To visualize this, we use t-SNE to compare MCCG and MCCG DPHR on 20 randomly selected satellite-to-drone queries. The results are striking. In MCCG, hard negatives often cluster right next to the query, even at rank 1. That's a failure. But in MCCG DPHR, those hard negatives are pushed farther away, creating a clearer separation. This isn't just statistical, it's geometric. The model learns to care about the right things. So what's the takeaway? Cross-view geolocalization isn't just about matching images. It's about learning robust, discriminative representations in the face of massive viewpoint, scale, and appearance variation. And the key: don't treat difficulty the same across time. Don't assume all hard negatives are equally hard. And don't trust the model's own confidence early in training. DPHR does all three. It introduces a relative, ratio-based measure of hardness, so difficulty is consistent across scenes. It applies progressive, adaptive weighting, so the model learns stability before sharpening focus. And it does it all within a standard triplet loss framework. No complex architecture changes, no extra parameters. This means DPHR is plug and play, easy to integrate into existing CVGL pipelines. In short, DPHR isn't just another loss trick. It's a principled, adaptive, and robust strategy for handling the real-world messiness of hard negatives. It works better, it's more stable, and it generalizes across datasets, models, and viewing conditions. And in a world where drones, satellites, and autonomous systems need to find their place in the real world, that's not just useful. It's essential. So next time you're building a geolocalization system, ask yourself, are you mining hard negatives, or are you understanding them? Because with DPHR, you don't just find the right image. You learn why it's right.